morning, everyone. Any questions before we start? Okay, so today we are going to talk that what we start 5G. Is this the improper integral, Wyatt?
No.
What is this? What is this 5G from?
It's from the review for the exam.
The review or the worksheet I gave you yesterday?
It's not off of my lab. It was off of Brightspace, just for the review.
Okay, tell me the integral. I don't have it in front of me.
No, we can come back to it then. I don't have it.
Okay, all right. So we'll come back to it. Sorry, I didn't put it in front of me yet. Okay. So let's go back to the idea of improper integral. Okay. Right. So let me a little bit quickly recall what we did yesterday. You don't have to write, just repetition, and then we start the formal definition of the improper integral. So what we did yesterday is the following. We took the following infinite area. So we had that. This was the graph of the function 1 over x squared. This was 1. And we took this infinite area. I mean, it goes on and on and on. We didn't really stop at all. And the question is, okay, what's the area of this region? I mean, what do we mean by this area? I mean, is it infinite? I mean, what's really going on? It keeps going forever. Is it infinite? And the way we did it, we say, we don't know. So we started computing those little areas. So we computed the integral from 1 to 10. So we computed this area of 1 over x squared dx. And then we got by antiderivative. And then we did it up to 100. So we did the same thing all over again. Antiderivative, we got 1 minus 1 over 100. And then we did it again up to 8,000. And we got 1 over minus 1 over 8,000. And then we agreed, we can keep going forever, but the answer is getting closer and closer to 1. So we say, okay, the area of S that we are going to denote it integral from 1 to infinity. So it's very reasonable to write that the area of S equal to 1. And it's very reasonable to write integral from 1 to infinity. But as I mentioned yesterday, in this process, we actually repeated the same thing 3 times. So we computed the antiderivative of the same function. What we changed is the upper bound, the upper bound, the upper bound. So the idea is now the following. Instead of doing this several times, why don't we do this? First, we compute the integral from 1 to t. So I call this upper bound t. 1 over x squared dx. So we find a formula for the integral, for the area, up to a finite number. So that's what we're going to do. So up to a finite number, t, why don't we find a formula for the area? So we compute this integral. And then if we do that, we get minus 1 over x between 1 and t. So which gives me minus 1 over t minus minus plus 1, which is 1 minus 1 over t. So instead of doing it, we say, okay, why don't we find a formula for the area in function of the upper bound? And then when we do that, so if t is 10, 1 minus 1 over 10. T is 100, 1 minus 1 over 100. T is 1,000, 1 over 1 minus 1,000. So we get a formula for the area in function of the upper bound. Then we say, okay, let this t go to infinity. Then we let t becomes very large. After we evaluate this finite area, then we let the upper bound become very large, will become equal to 1. So what we actually do to basically simplify the work, we say we evaluate the integral from 1 to t of 1 over x squared dx. That's really mathematically what we do. Once we find this area, then we say, okay, let us take the upper bound, go to infinity. That's really what we are going to be doing. And then this will be the area of S. Right? So that's the motivation of the definition. And this we're going to denote it. This limit, we're going to denote it by the integral from 1 to infinity of 1 over x squared dx. So we're going to give a definition for this integral from 1 to infinity that we are going to call improper integral, because that's an integral over, it's an integral over an infinite domain. We're going to give it definition to be the limit of those finite integrals. Right, so now I'm going to state the definition clearly, and then we're going to do a bunch of problems. And if I have time, I'll go back to a y-x problem. Okay. So now the formal definition for any function, not only 1 over x squared. So I will write it, put it here, and I will read it carefully so I don't have, and we proceed. So the formal definition. Since you guys are writing, I'll read it very, very slowly. So let f of x be a function which is continuous over the interval a to plus infinity. So I have a function from a to plus infinity is behaving very nicely. Okay. Then that's our definition. Integral from a to infinity of f of x dx. Remember, as I mentioned yesterday, the Riemann sum, integral from a to b, the definite integral is defined as limit of Riemann sum. Riemann sum requires us to divide the interval into pieces. When I have an inbounded interval, the definition falls apart. It doesn't work. So it's equal to the limit as t goes to infinity of the integral from a to t of f of x dx. So to help you with the picture, that's really my picture right here. That's my function. This is my a. It could be a, it could be negative. This is my t. We evaluate the integral up to t. We find a formula for the area, and then we let t goes to infinity. So it's the limit as t goes to infinity of the integral from a to t of f of x dx. We don't use the same variable. We use x here and t here so we don't get confused. Provided this limit exists, because this limit could be plus infinity or it doesn't exist. So we define it to be the limit provided this limit exists. Now, the same token, we talk about the integral from minus infinity to b. So now 2. Let f be again a continuous function from minus infinity to b. So suppose I have this type of function. This is my b up here. Then we define the integral from minus infinity to b of f of x dx. So it's the same approach. We find the integral from t to b, and then we let this t go to minus infinity. Integral from t, the lower bound is t, the upper bound is b now, f of x dx, the limit as t goes to minus infinity. Right. Now, a new word that we're going to start introducing. Well, if you're finding the limit may or may not exist, simply because the limit could be plus infinity or it doesn't exist. Now, we will say the following. If the limit exists, we will say that the integral converges. So let us read that. In each case, if the limit exists as a finite number, remember we're computing the limit and the limit may not exist. If the limit exists as a finite number, then we say that the improper integral, so this integral is called improper. Then we say that the improper integrals, integral from a to plus infinity and integral from minus infinity to b, the improper integral, are convergent. So that's a new word you're going to hear a lot of it since now. Convergent. So if the integral exists, convergent. Otherwise, we say they are divergent. So if the improper integral exists as a finite number, we say that it's convergent. otherwise divergent. One more definition, and then we start working out problem. 3. Suppose sometimes we talk about the integral from minus infinity to plus infinity. So let's see the definition of that clearly. Let f be a continuous function on the interval minus infinity plus infinity. Then, integral from minus infinity to plus infinity of x dx is defined to be integral from minus infinity to 0 plus from 0 plus infinity. So provided that both integral converge. So from minus infinity to infinity, we defined it to be the sum from minus infinity to 0 if both converge. If either diverges, then we say that the integral diverges. Okay. So now once we write the definition, and then we can take example. But the definition is crucial, we're gonna work with it. So this tells me that if both converge, because this is an improper, because the domain is not finite, it's infinite, so it is called an improper integral. If this one converge and this one converge, we say that minus infinity to plus infinity converge, and it's equal to their sum. If either one diverge, we're done. The integral diverges.
Oh wait, I have a question. Did you say if either of them diverge?
We're done.
Where?
It diverges.
Okay.
Either
So-
diverge, we say that the integral from minus infinity to infinity diverge. So if one converge, one diverge, the whole thing diverge.
Okay.
That's the definition. If both converge, then we say that the integral converge. And its value is the sum. So it's minus infinity to 0 plus 0 to infinity. Yeah, usually it's confusing for the student. No, if one of them, this one diverge, the whole thing falls apart. We're done. If this one diverge, the whole thing diverge. That's the definition.
So okay. So for both of them to be diverge, then it'll be divergence.
Of course, if both diverge, the whole thing diverge. If one of them diverge, the whole thing diverge.
All right.
That's the definition. Okay. All right. So now let's take up example. So it's crucial. So this improper integral, that's called improper because it's not your regular integral, because since the domain is infinite, so it's not our regular integral, is defined to be this limit. So we're going to now take some problems, bunch of them, to make sure we understand the definition. So example right now. So example number 1. So this section is not really hard. It's just a matter of integrating and finding the limit. So let's get going. Suppose my question now is determine whether the following integral from 1 to infinity of 1 over x dx converge or diverge. And it's going to be the same question for diversion. And show your work as usual, and so on and so forth. All right. First, we start with the definition, and that's crucial. What's the integral from 1 to infinity of 1 over x dx? Okay, so now I have basically the same picture as before. That's the graph 1 over x. That's a 1, and I'm looking at that. And the question is this area finite or infinite in this case? Step number 1, 1 to infinity doesn't make sense. The definition is, memorize the definition is easy. You find first the finite integral from 1 to t of 1 over x dx. Once I compute this one, then I take t to infinity. So the first step is we find this finite integral, then we let t goes to infinity. Okay, so it's equal to, now this is a simple integral I'm starting with. 1 over x, the antiderivative is ln from 1 to t. Okay, so it's equal to the limit as t goes to infinity of ln of t minus the ln of 1. Now the ln of 1 is 0. So it's going to give me the limit as t goes to infinity of the ln of t. So what does ln of t represent in the picture? Anybody? What does ln of t represent in the picture?
Isn't it just infinity?
What?
Infinity?
The limit is infinity, but this expression by itself, what does it represent in the picture? Here.
Area under the graph
Exactly. Up to where?
between 1 and t.
Exactly. It represents this area. So the area here, that's really the picture. This area is ln of t. So that's what we are doing. We are evaluating the area up to t. And then we say, okay, if t equals 10, that's where the idea of starting to push the value of t. 10, 100, 1,000. That's what we're doing. So instead of doing that, we say, what happens when t becomes very large? And that's the limit. And now what's the limit of ln of t when t goes to infinity? Remember, I made a quick review yesterday, so we know all those limits. What happened to ln when t goes to infinity? Guys, remember? This is the graph of ln. So when t goes to infinity, the limit is equal to infinity. So ln of t, when t becomes very large, ln of t itself becomes very large, but very, very slowly, but it becomes very large. So what can we say? It means that the integral diverges. So if the limit does not exist as a finite number, then in this case, we say that the integral diverges. So it's very, actually, it's interesting that if I do those, I mean, that's actually interesting and counterintuitive in a way. So when I took 1 over x squared, as an example, this really turned out to be 1. But when I take 1 over x, this area actually goes to infinity. Okay. So it's hard to explain what's going on without computing the value. So I cannot, when I see a function, tell you what's going on. But intuitively, why is it possible for this to be 1 and this one could be infinity? What's the main difference between both functions? What's the difference between both functions that make this one, even you go to infinity to be 1, but this one actually go to infinity is really still very large? Okay, give me one difference between the function.
The second one goes to infinity slower.
Exactly, it's a matter of growth. 1 over x goes to infinity way slower than 1 over x squared. It doesn't mean I know which one goes, but I'm trying to compare the growth of the function. So this one goes to infinity. When x getting very large, when x gets large here, so for example, 100, this is 1 over x squared. So this is 1 over 1,000 squared. So this goes to 0. This goes to 0 way faster than this function goes to 0. If I take here 100, for example, from here to here is 1 over 100. However, this is 1 over 100 squared. So this one goes to 0 much faster than this function goes to 0. That's the only comparison I can make between those functions. Okay, that's really what's happening. So the faster the function goes to 0, the more likely the integral to converge. But we don't know just by looking. We have to do the math, but it has to dive to 0, go to 0 very, very fast for the integral to converge. Otherwise, it makes sense. The area still add up, and it blows up to infinity. So we're going to do, as I said, several examples to elaborate this idea. So example number 2 is the following. So it's a matter of first evaluating an integral, and then it's a matter of computing a limit. So evaluate the following integral, another one, integral from 1 to infinity of e to the minus x dx. And the question is, does this integral improper, because it's an infinite domain, does it converge or diverge? And check it out. So as I said, when I look at it, I have no idea. The only way I can do that is by evaluating it. All right. And when you evaluate it, it's crucial. It's a limit. So here, I don't want to see infinity because I don't know what it means. You don't know either. We have to go by the definition. So that's the definition. We compute the area up to t. We find the formula for it. And then I let my t goes to infinity. Okay, that's the only way to do it. All right. So now we have to evaluate the integral. Okay, e minus t, I would like to do it here on the side just to make the problem a little bit so I don't mess up with the limit. What's the antiderivative of that? Oh, sorry. X. Do we know what's the antiderivative of this function? Have we seen this before? Very quiet.
X e raised to the raised to x?
No.
Or negative x?
Yeah, this is, let me write this, e to the minus x. It's equal to. It's not e minus, it's minus e minus x. Let us do a little bit of simplification. So let me even forget the limit. Let me do a substitution. U equal minus x. du is minus dx. So it's become minus the integral of eu du. It means minus e to the u minus e to the minus x. Okay, so this integral is minus e to the minus x. Be careful. So now it's going to be minus e minus x. So I evaluated the limit on this side to make things easy for us, equal to that. All right, so it's equal to limit as t goes to infinity of minus e minus t minus minus plus 1. What's this limit? So this is my graph here, e minus x, 1. I don't know why I'm picking 1 every time. I don't have to. So that's really the graph is also a decreasing function. Now what's this limit? What is this limit? I give you a second to interact with it because we have to by now, starting now.
Is it 0?
Why 0? Let's justify every word. Why 0?
Well, I know that the limit when x approaches infinity, e to the negative x is 0.
Very good. So what happened to plus 1?
That stays on the left side, correct?
Forget about that. Yeah, plus 1. So when t goes to infinity, what happened? First, it cannot be 0. Why it cannot be 0? Because it's this area. That's e minus x. That's the function. When you evaluate from 1 to infinity, you're actually computing this area. It can't be 0, period. That's first answer number 1. So let us evaluate. So I'm having a correct answers on chat. Equal. As I did yesterday for e minus t, I rewrote it like this. And then what happened to that? When t goes to infinity, e to the t goes to infinity, this term will have to go to 0. So this becomes very close to 0, but I have plus 1, so this is going to be equal to 1. So the integral converges, and the value of the integral is 1. So integral converge. and it's equal to 1. That's its value. Okay, so it converges and its value is equal to 1. Right, so as I said, we're going to do a bunch of problems. I will do at least 2 more problems along the same line.
I have a question.
Yes.
So converges is when an answer actually has a solution?
Yeah, it's a number. It's not infinite. So
Okay.
it's a finite number. If you go back to my definition, finite number. So this was 1, it converges. This was infinity, it diverges. All right?
Yeah, thank you.
Sure. Thanks for your questions, actually. All right. Same question, but now I want to integral. I'm going to change a little bit. So let me take from minus infinity to 2, for example, of 1 over 1 plus x squared dx. Okay, and the question is, so example number 3, the same, converge, diverge, whatever. All right, again, the definition is the definition. You cannot do those problems without writing the definition clearly. So this is going to be equal to what? All right, who would like to tell me? So that's improper because the domain of integration is infinite. So how we're gonna, what's the setup?
Isn't it upper limit 2, lower limit t, 1 over 1 plus t squared dt?
Why? Why you don't put t inside?
Oh, okay.
The same integral. Don't put t inside. You find this area. But then what you do to t after that? Keep going. After you evaluate this integral, then what do?
Don't you make it a limit of t going to infinity?
Which infinity?
Oh, negative infinity.
The first step. Extremely important step, otherwise it will not make sense to us. Okay, so that's the setup. So it's the same picture. 1 plus x squared, it's a function, it dive at minus infinity, that's my 2. This is 1 over 1 plus x squared, and that's the area I am interested in. Okay, so I evaluate it from t to 2, and then I let my t get more and more negative. All right, so now let's evaluate the limit. Now, 1 over 1 plus x squared, I'm still taking simple antiderivative. What's the antiderivative of 1 over 1 plus x squared? Quickly. Quickly, guys.
Is it the natural log of 1 plus x squared?
Why?
Can we substitute 1 plus x squared for u?
Can we? If we do, what do we get?
Tangent. Inverse of tangent.
That's inverse tangent. Why we cannot substitute? You substitute, what's going to be the derivative? X dx, right? There is no way to pick up the derivative in here. So that's 1 over 1 plus x squared, that's arctangent. X evaluated between 2 and t. Okay, so that's the arctangent. All right, so it's equal to the limit as t goes to minus infinity of. So the only difficulty in those problems is that you have to integrate and you have to find a limit. Okay, but we have to get ready for that anyway. So it's going to give me arctangent 2 minus arctangent of t. Arctangent 2 is a number. You know, we pick up our calculator, we find it. I don't really care about it. Now, my question is, what's the limit? When t goes to minus infinity of arctangent t. Means what's the angle whose tangent goes to minus infinity? So this will give me, that's arctangent 2 minus. Now what's happening to that? So I'm looking for the angle whose tangent go to minus infinity. Anybody has any recollection?
It goes somewhere to -90.
Exactly, to -90. So which is, in calculus, we don't use degree, we only use radian. Means minus pi over 2. So let us remember the graph of it. We don't remember the graph of arctangent. I don't, but I really remember very well, and this is crucial for us to remember the graph of tangent. So that's really the graph of tangent. So what we are doing, so when the tangent of any angle goes to minus infinity, when the angle goes to minus pi over 2. So this is pi over 2, right? Minus pi over 2, and that's where the tangent. So the arctangent is going to go to minus pi over 2 when t goes to infinity, because it's the inverse function. So when t goes to minus infinity, the arctangent goes to minus pi over 2. So this angle, the value would be arctangent 2 plus pi over 2. Now this is a finite number, then it means that the integral converges. And the value of this integral, the definition of it is the arctangent 2 plus pi over 2. It means basically this infinite area, it's not infinite, this infinite region, if you want, its area, very counterintuitive. You say, you're going to infinity, the area has to be infinity, and then it's me, no, this area here is actually equal to arctangent 2 plus pi over 2, even if you keep going forever in the negative direction. I'm going to do one more problem along the same line. So it's integration with limit, which is make it a little bit hard, but not very hard. So now let me take, since I'm running through all the problem, integral from minus infinity to plus infinity of x e to the minus x squared dx. Okay. All right. So this problem, it has an improper integral, as you really realize. But I have minus infinity and plus infinity. So what do we do in this scenario? What do we do in this
we
scenario?
have to like separate them
Right.
for t negative infinity and then.
Okay, so in this case, we're going to look at two integrals from minus infinity to 0. Now, actually, let me be, 0 is not important. You can go to minus infinity to any number, like 1 or 2, and from 1 to plus infinity. I picked 0 because 0 is a very easy number. So first, we need to look at this integral. So we have to analyze this integral, and we have to analyze that integral separately. Now, and then, if both converge, we're fine. If either diverge, it means the whole thing diverges. But you have to compute both of them. So let me start with the first one. Integral from minus infinity to plus to 0 of x e minus x squared dx. The only way to do it is we have first to write it as a limit. That's the following limit. It's the limit of, it's minus infinity. So the upper limit remains fixed. It's the lower limit that is going to vary. So I have to compute this integral And then I'm going to let the t go to minus infinity. So that's the definition. So now the problem is a question of evaluating this integral, which is going to be depend on the value of t. And then I will let my t become more and more negative. So on the side here, I'm going to first evaluate this one, e minus x squared, because it's not clear for me what it is. So I first evaluate that, and then I plug it into the value. So I'm going to isolate this integral without the limit. I'm not going to play with the limit. I'm going to leave the limit the way they are. So how can I evaluate this integral?
Use substitution.
Let's say use substitution. U equal minus x squared, du is minus 2x dx. And now be careful, since I am not, I'm not going to change the upper and lower limit, so I have to go back to x. So it's going to be equal to x dx is minus a half du. So this will give me minus a half, and I will have e to the u du. Okay. So this is minus a half e to the minus x squared. All right, so I isolated this integral a little bit because we knew that I had to do work with that equal to that. Now I go back to my piece right there. So now the infinite integral, the improper integral, is equal to the limit as t goes to minus infinity of minus a half e to the minus x squared evaluated between t and 0. So find this equal to the minus a half can be actually pulled out just to make our life a little bit easier. And inside I will have the value at the upper limit is e to the 0, which is a 1, minus the value at the lower limit, which is e, since I, to the minus t squared. Now finally, I will end up with the following. Limit as t goes to infinity of minus a half plus a half e to the minus t squared. And my t goes to minus infinity. So this is equal to what? Anybody?
Would it just be negative half?
It will be negative half. Yes, because.
Yeah, because e to the negative infinity is going to end up being 0.
Right, because this one. Remember, t goes to minus infinity. But here I have t squared, which is a positive number. Okay, otherwise, I will have problem. I'll mention that in a minute. So now here, because limit as t goes to minus infinity of e to the minus t squared is, as your classmate said, or if it's over 1 over t squared, if you want. Now, when t goes to minus infinity, t squared, because we're squaring, still go to plus infinity. So this is going to be equal to 0. And the integral is minus a half. That's a finite integral, absolutely. So this piece converges. And the reason we're having minus a half, because if we graph the function, if we graph x e minus x squared, the function looks something like that. It dips down, it goes up, and it goes something like this. So that's the reason we're having a negative number here. It actually makes sense. It does not contradict the problem. Are we done?
We need to find the other one now.
We have to find the other one. This one converges, so this one is safe. Now we have to find the other one. If the other one diverges, it means the whole thing blows up. If the other one converges, we are fine. Okay, so we have to go and do both of them. So we will do the other one, which is going to be quick because I already evaluated the antiderivative. So now we have to look at this piece. Integral from 0 to plus infinity of x e to the minus x squared dx. All right. So this is equal to, that's a improper, that's a plus infinity. So this is my t now, and that's my 0. And I will let the upper bound goes to infinity. And inside it's the same integral, e minus x squared dx. So here I have to, all right. Now I did already evaluate the indefinite integral. And we got minus a half e to the minus x squared, but now from 0 to t. Okay, so by evaluating this right here, we found the antiderivative, so I don't have to repeat it again. Okay. And now this is equal to fundamental theorem, that's what we're doing, of at the upper limit, minus minus, at the lower limit, we get a half. So finally, we get the following. The limit as t goes, sorry, we don't need limit anymore. All right, let us analyze this. When t goes to infinity, okay, so this is a constant. When t takes very large value, as we said, this piece here, again, will go to 0 for the same reason I mentioned before, because e to the minus t squared, you can think about it as 1 over t squared. So when t goes to infinity, 1 over t squared goes to 0. I will have 0 plus a half. That's equal to half. So this one also converges. Okay. So since both converges, since the integral from minus infinity to 0 of x e minus x squared dx and integral from 0 to infinity of x e minus x squared dx converge, then the whole thing converges. Because we have in n, both of them. Converge. And the value of this integral, so it's converged, but what's its value, as our definition is the value of the first plus the value of the second. And in this case, it happened to be a 0 because the function is taking positive and negative value.
I have a question. Say like on a exam or something,
Yes.
if we find the first one is diverging, do
You
we just
stop.
stop there? Okay.
Exactly. You stop.
All
One
right.
diverge, you're done. You don't have to move on any further. And that's it.
All right.
Both have
Thank
to.
you.
That's the definition. Both have to converge, otherwise it doesn't make sense. A diverge. Okay.
All right.
All right. So these are the idea for this improper integral. So let me now talk a little bit about some simple one. So let's see, what we saw at the beginning is that integral from 1 to infinity of 1 over x squared dx converge. Remember that? And we saw that the integral from 1 to infinity of 1 over x dx diverge. Okay, and usually the question is, if we have integral of this form, 1 over x squared, 1 over x cubed, 1 over root x, it's nice to know what is the cutoff. I mean, when things start converging, when things start diverging. So I'm going to give you two problems, and then I will see if I can give you the root today. Suppose I'm going to take 1 over square root of x dx. I'll give you a minute to tell me whether this integral converge or diverge. What did you guys find out?
I think it diverges.
Okay. All right, so let's do it. Is the limit as t goes to infinity of integral from 1 to t. Since we know we have to evaluate, I have to write it this way. Okay, so this is gonna give me the limit as t goes to infinity of 1 over minus a half plus 1, it's a 2, x to the power a half between 1 and t. Are you with me? So this will give me the limit as t goes to infinity of 2 square root of t minus 2 square root of 1, which is 1. So this is going to be equal as t goes to infinity. This is blowing up. This go equal to infinity. So it diverges. So 1 over root x diverge. Now I'm going to give you another one and see, suppose I give you 1 over x to the power, I don't know, 1.1 dx. Converge or diverge?
Does it diverge?
Diverge, okay. Why? Did you do the whole thing?
It's because it's ln of infinity.
I will not answer unless I evaluate. Are you with me? I evaluate. This is not the infinity. The infinity does not mean it diverge. It's the limit of x to the power 1.1. I know that I've never given you something like that. So I'm gonna, the only way is to do it this way. It's x to the power, we're gonna do it this way. So it's equal to of 1 over minus 0.1 plus 1 x to the minus 0.1 plus 1 between 1 and t. So it's equal to the limits. As you realize, I don't know the answer. I have to do the math. Minus 1.1 plus 1, that's going to give me minus 0.1 x to the minus 0.1 evaluated between 1 and t. So finally, it's going to be the following. Fundamental theorem of calculus. So this is 1 over minus 0.1, it's minus 10, right? So it's minus 10 times t to the minus 0.1 minus plus 10, 1 to any power is 10. So now it's up to you. Does this converge or diverge? analyze the way I'm trying to do. We have to start analyzing limit. That's where we're heading toward. So what do you think?
It converges.
Converges because
To get rid of the negative power, you put 1 over t to the 0.1.
Here you are. So that's negative. And I'm trying to put negative power in the denominator because we know how to interact with it. I know the 0.1 is bothering you, but you guys are moving, advancing. And now when t becomes large, t to the power 0.1, even though it's a weird power, it's the 10th root. So 0.1 is 1 over 10. So t to the power 1 over 10, you're basically talking about the 10th root of t. That's really what you're still talking about. So when t becomes very large, the 10th root of t will actually still becomes very large. So when t goes to infinity, what's going to happen? This one goes to infinity. The whole thing will go to 0. And this is equal to 10. Absolutely converges. Okay, so do not guess before integrating because it's not highly intuitive without computation. So I cannot look at the improper integral, tell you whether it converges or not. I have one way to do it. This only way is to evaluate the integral and then proceed. So it definitely converges. All right, as usual, I'm 2 minutes. Wyatt, you can stay with me. I can go over the problem you asked, if you don't mind. And any questions? So please do your homework for tomorrow. What I do today and tomorrow will be absolutely on your exam. And integrate. All right, the class is dismissed. Wyatt, can you stay with me?